Hey guys, today we're going to continue our study of the polar coordinate system by studying the graphs of polar equations. We're going to start with this equation right here. R equals 4 sine theta. Now, I cheated a little bit, and that might hurt you ultimately, but this, if you did all the hard math, this is the table that you would generate if you were asked or called to do this by hand. But I just want to do a few of these values and R, and guys, I know I wrote those, I put the theta first, and it is supposed to be R comma theta, but when building this table it makes more sense because theta is independent and independent usually comes first. So this was not a mistake, but hopefully it'll help you understand more. So my left column is this top row. So as I write these things, 0, pi over 6, pi over 3, pi over 2. Now, what can I do with those? Well, if it's an independent variable, it needs to be plugged in, and if it needs to be plugged in, well, then that's what I should do. So 4 times sine of 0, 4 times sine pi over 6, 4 times sine pi over 3, 4 times sine pi over 2, and so on and so forth. Now, when you simplify that, all of those values, then you're going to get the following. The y value at 0 radians is going to be 0. 4 times 0 is 0. The y value at pi over 6 is going to be 1/2, so 4 times 1/2 is 2. The y value at pi over 3 is root 3 over 2, and 4 times root 3 over 2 is going to be 2 root 3. And then 4 times the sine value at pi over 2. Well, the sine value at pi over 2 is 1, so 4 times 1 is 4. You'll notice that these values match these values. So if I ask you to do this by hand on the quiz coming up, you have an idea of how to do it. It's all about function basics, and you have an input and an output. Plug in the input, it pops something out, that's your output, that's how it works. So what we're going to do is we're going to go ahead and plot these points as we go along, and we're going to see what happens, and we're going to use our knowledge of symmetry to facilitate us in this process. So I'm going to go ahead and pause the video. I'm going to mark or indicate all the thetas that are indicated in the table, and then I'll be right back. I like to do that because looking at a polar coordinate system can kind of make you dizzy sometimes, and there's lots of easy ways to make mistakes, and especially towards the middle of it, the lines converge and it's easy to get tripped up, so it helps me keep track of things and make the fewest mistakes possible, which is what it's all about. So let's plot these things. 0, 0, boom. We got pi over 6 and 2, not too bad. We got pi over 3 and 2 root 3. Is going to be approximately 3.46. So I think that's close enough for to 3.5 for our purposes. 1, 2, 3.5. Then that goes all the way to 4. And we can come back and use our knowledge of symmetry to do something like this. And if we kept graphing, it will create a circle. Now, technically, when I started drawing the circle, I had only gotten halfway on my table. If I do these other graphs, then or these other locations, what's going to happen is it's going to plot another circle on top of what we already have. So again, if I go to 7 pi over 6, well, how that works? Here's 7 pi over 6 here, but look, I have a negative radius, so that means go the opposite direction 2 rings. Oh, right there. And then let's do the next one. 3 pi over 2 is 7 pi over 6. Oh, we skipped one, didn't we? 3 pi over 2 is right here. If I have a negative radius, so I got to go the opposite direction to negative 4. Oh, these points are lining up quite nicely. Then same thing, 11 pi over 6. We have a negative radius, so I got to go the opposite direction to that negative 2. And there, one period of sine in a polar coordinate system is actually going to be 2 circles that coincide, just like that. Now, circles are one thing you can graph, and we're about to discover some of the other names and families of graph shapes that Polar is able to give us. And after we graph this, we'll talk about that vocabulary in a minute, but the nuts and bolts and functionality are all still the same. Step one, let's build a table. Okay. I know it's always supposed to be r comma theta, but theta is independent. Don't ask me why they're switched. I asked somebody today, and she didn't know either, and she's smarter than me, so it works out. But I promise I'll figure out why. I'll find the math guru of all gurus to figure out why the independent variable is listed second when we have polar coordinates r comma theta. Okay, so let's plug in our values: 0, pi over 6, pi over 3, and so on. And I cheated. And the reason I'm doing this is, well, what if on the quiz, I'm likely not going to cheat and give you the table, and I don't want you to be like, well, but Mr. Watkins gave me the table on the notes. No, you need to know how to do it. So we take our function, and we do what it says. So my output's going to be 3 plus 2 times the cosine value at the angle in question. So in this one, 0, so I plug in 0 here. 3 plus 2 times cosine pi over 6. 3 plus 2 cosine pi over 3, and so on. So let's evaluate this stuff. 3 plus 2 times the cosine of 0 is 1. 2 times 1 is 2. 3 plus 2 is 5. Oh, look at that. I'm not lying to you. Cosine of pi over 6 is root 3 over 2. Root 3 over 2 times 2 is going to be root 3. And then 3 plus 2 times root 3 over 2 is just going to be 3 plus root 3, because those cancel out. Let's do one more just for fun. Why don't we? 2 times cosine at pi over 3 is 1/2. That's a times. 2 times 1/2 is 1. 3 plus 1 is 4. Yay, I'm not lying to you. But so that's how you would go about generating this table on your own come quiz day or test day. So let's use these values and then see what it does, and it's going to do something different than just give us a plain old circle. So let's plot our values. I'm going to go ahead and pre-draw my thetas just to help keep track and minimize mistakes. And I'm back there. My thetas pre-drawn. They're indicated again. Help minimize mistakes, clean it up a little bit. And so let's plot our points. We have 0 radians and radius of 5. We are plotting this point, so 0, 5, go out 5 rings on 0 radians, 1, 2, 3, 4, 5. Hello. Then 3 plus the square root of 3 is not something that's right at the tip of my head. I should probably have those memorized, but that's going to be 4.73 approximately. And 4.73 is going to be really close to that, really right just inside that 5th ring. We're going to go 4 on the next one. We're going to go 3 on the next one. We're going to go 2 on the next one. We're going to go 3 minus root 3. 3 minus root 3 is 1.26. And so on my next one, I'm going to go right there. 1.26. And then we're going to go 1 on my next one. And then we're going to use what we know about symmetry. And this is going to have, if this were rectangular, we'd say it has x-axis symmetry. But because it's polar, we're going to say it has symmetry about the polar axis, because our graph starts at 0 radians there. So what's going to happen? Well, for every point on top is going to have a corresponding match below, and it is, hold on, I'm working really hard here, folks. There we go. So let's see what actually happened, and I'll use a blue color. If you notice, it's not a circle. It's called a cardioid because it makes kind of a heart shape. So generally we draw hearts like this, but you can kind of see that this part here kind of goes with this part here, it dimples in, right? So, did we use symmetry to sketch that graph? Yes, we did. We plotted the top half, and then we reflected across the polar axis. And yeah, we learned a new shape called a cardioid, and it's called a cardioid because it looks like a heart. All right, folks, let's do this one more time. My last polar function of the day is this r equals 2 cosine 3 theta. I cheated, remember, I'm giving you the tables, but on the quiz or the test, you won't be given the table, so let's talk about where these numbers come from. Okay, these numbers come from taking my independent variable, my theta, plugging these numbers in, pi over 12, pi over 6, and these are all increments of pi over 12 is being added each time, so pi over 4, pi over 3, pi over 5 pi over 12, I'm sorry. That's not a typical value, hence the goof, but no excuses, right? I need to be better. And then pi over 2. And I'm not going to fill all these in, don't worry, never fear. But what do you do with independent variable? You plug it in. Independent variable is also known as an input. Then you plug it, once you plug it in, we get an output, or the dependent variable. So 2 times cosine 3 of theta, which is going to be 0. 3 times 0 is 0. Cosine at 0 is 1. 2 times 1 is 2. Did I lie to you? No, I didn't. We're good. Okay. Check. Let's do it again. 2 times cosine of 3 times pi over 12 is a value that's less familiar to me, but that doesn't mean we can't do it. I'm sorry. I'm so silly. 3 times pi over 12 is really pi over 4, and I'll take an extra step. Cosine of is 3 pi over 12, which simplifies to pi over 4. I do know cosine of pi over 4, which is root 2 over 2. So 2 times root 2 over 2 is just root 2. Did I lie to you? Nope. That goes there. And let's try one more, pi over 6. 2 times cosine of 3 times pi over 6. Should have put these in parentheses while I'm thinking about it. Okay, so 2 times cosine of 3 times pi over 6 is really going to be pi over 2. Cosine of pi over 2 is 0. 2 times 0 is 0. So guys, you can do this. I know it's a little bit of work, but the hard work pays off if you put in the memorization skills on the front end, or the mental math skills, or the multiplication skills. It all pays in. There's really no shortcuts to any sort of strength, whether it be physical strength, brain strength, math strength, all of that good stuff. So let's plot these things and see what happens and see what we get. 2 cosine 3 theta. So we're plotting each of these individual points. The table is horizontal, but that's not going to scare us. I'm going to indicate my theta values real quick. There, all the thetas have been indicated, so that's going to hopefully help me in the very near future. So let's get it done. As I'm plotting these points, I know that 0 goes with 2. Find the second ring at 0 radians. Then I know that root 2 goes with pi over 12. And root 2 is 1.414. So I'll go 1 point, a little less than halfway there. And then pi over 6 is 0. Then pi over 4 is negative root 2. So here's my positive pi over 4. And let me go this way. Here's my positive pi over 4. But a negative radius means you go the opposite direction towards 5 pi over 4. And then once you've gone the opposite direction, then you can trust the number again. I'm going to go negative root 2, so that's going to be negative 1.4, about right there. Then we're going to go pi over 3, which gives me would normally be this way, but since I have a negative radius, then I'm going to look for negative 2 on that line that I just dotted. And then we're going to keep going, negative 2, and then same thing, 5 pi over 12 would normally be here, but the negative radius means we go the opposite direction towards 17 pi over 12. That's not a value you normally see on a unit circle, but alas, it's there. And then, and then I need to not get distracted. 5 pi over 12, negative root 2 over 2. So let's go ahead and plot that, or sorry, negative root 2. So that's going to be right there. And we'll go back to pi over 2 and 0. Okay, so let's look at what just happened. And I want you to pay close attention in real time. We went here, 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 and here. So what I want you to see, and we're going to use some knowledge of symmetry about the origin to reflect some of this stuff. Now, what I want you to see is we can kind of deduce that there's going to be a dot right there, and then not only that, these things are separated by 2 pi over 3, so if it's 2 pi over 3, then this I know is going to go up there. We'll have corresponding values here and here. And by using symmetry and a little bit of content knowledge, let me show you what we're doing. I'll start tracing in green. So remember, we started here, then we came over here, we came over here, and then we finish our curve right there. It's a little wonky, but it's going to be okay. Now that is a rose curve with 3 petals. Sorry, not bike pedals. And when you're, how do we know it's going to be 3? Well, you can trust, so whenever your coefficient of theta, that I just indicated right here, is odd, you can trust it. Whenever it's even, you have to double it. So those are good things to keep in track, keep track of. But guys, thanks for paying attention. Thanks for hanging in there. Oh, one last thing. Let's look at the next page. These are all the different names for graphs you can have. Now, there's several different categories. We have limacons. That includes a cardioid, which we graphed earlier. We have rose curves, and we have different kinds of rose curves and how you make them. And then we have circles, which we're familiar with, and then lemniscates, which look like an infinity sign. So all you need to know from here is to be able to, if you saw a generic picture of one of these, so if I gave you that picture, you need to tell me that it's a cardioid. If it's a, if you see this picture of a flower, you wouldn't call it just a flower, you'd call it a rose curve. If you see this one right here, you'd call it a lemniscate, and then obviously that's a circle. That's it for today, guys.